Okay, I would say we start. Hello, welcome everyone to the next lecture. So last time we proved, or modulo some lemmas, we proved Mordell's theorem that the group of rational points of an elliptic curve is finitely generated. And what we want to do today is prove lemma 3 that we used and give an idea of the proof of lemma 4, where we leave out all the technical stuff and only give the idea. So I'm not wearing shoes and I forgot that everything's wet here, but maybe. Okay, what was lemma 3 about? Lemma 3 was there is a constant k depending only on E such that this holds. Here we have to be a bit careful because here we use the logarithmic height. But in general, there's not a big difference between the two versions of the height. It's just how we write them down if we want to play around additively or multiplicatively. So, as already in the last lemmas, here it's also okay to exclude finitely many p, because finitely many p have a bounded height, and then we can just adjust our k. So for this part, we exclude the two torsion. So P is not a rational two torsion point. And then we just want to look at the coordinates of P and 2P. Remember that the height of a point is just the height of the x-coordinate. So we have to look at the x-coordinate. So let P be xy and 2P zeta eta. And then our formula for doubling a point gives the following. And we can multiply that out. Did I make a mistake?
I just couldn't read what's already
yeah, our formula. Yeah. So we can, of course, because the points lie on the curve, we can always take, instead of y squared, we can take x cubed plus ax plus b, and this we keep it like this. So now we put the 2x on the other side and have then if we multiply the 2x by this, we get So this should be correct. We have minus 2x squared. Minus 2x. Here we have the 4 times x to the cube plus 9x to the 4 gives our x. Then this is the 6x squared a minus 2x times 2ax. Yeah, it should be right. And this is the rest. Oh, and here's probably a square missing. There should be a square here, right? Yeah. Oh, is this now correct? This is. Okay, let's try if it still fits. Okay, so yeah, actually we wouldn't actually have needed all of this because here, so this is f prime of x, and this is actually all that we want because so we have here our minus 2x times f of x, and now we have x prime, and here we have 4f of x. Oh, so yeah, this is actually not at all needed, I think. So because our point is not a 2 torsion point, this is not 0. So this is valid to look at. And also we have that since the discriminant of the curve is not 0, this is equivalent to the polynomial f and f prime of x not having any common zeros. So those two are co-prime. Those two are co-prime. So the numerator and the denominator are also co-prime. Okay, so what do we want to look at? We want to look at the height of the x-coordinate of 2p and the height of the x-coordinate of x. So the height of the x-coordinate of 2p is this. We want to compare the heights. Namely this. And this. And we want to allow some constant k that depends only on E. So we will reformulate this. So this is now a break in the proof, and we will put in another lemma in between, lemma 3 prime, and we will formulate this what we want to show for general f and f prime basically. So we have two polynomials. two polynomials with integer coefficients, and the polynomials should be co-prime, so that's just what we have here. And then we want this. So then we want that the greatest common divisor of n to the d times phi of m over n and n to the d times psi of m over n divides this r. So we basically clear out all the denominators with this n to the d, because d is the maximum of the degrees. And after we cleared all the denominators, then the greatest common divisor should still divide some integer r that depends only on the polynomials and not on what we plug in. And what else do we want? So the other thing that we want is when we plug in a rational number, then the height of phi of this rational number over psi of this rational number is bounded by something that depends only on the height of what we plug in, on the degrees, and some constant that depends on phi and psi. Yeah? Yeah, not roots of psi, phi and psi. Yeah. Yeah, I wanted to save space, which maybe wasn't a good idea. Yeah. Okay, so let's start with part A. Since d is the maximum of the degrees, we definitely have that n to the d times phi of m over n and n to the d times psi of m over n are integers. Oops. So it makes sense at all to look at a GCD and dividing things. Since everything that we want is symmetric in phi and psi, because this is also symmetric since the height of the inverse is the same as the height of the element itself, we can also assume that one of the polynomials has degree d. And we take phi phi to be this one. And the degree of psi, we call it E. This can also be D. So no one is saying that they cannot have the same degree. So let's write them down. And the same for psi. And since we want to play around with these terms a lot, we give them new names, namely capital phi of m comma n and capital psi of m comma n. Okay, so we have as a condition that they are coprime. So coprime with polynomials means that they have no common root. So we can use the Euclidean algorithm and find some Bézout coefficients. Such that this holds. Where f and g are polynomial integral polynomials. No. Rational polynomials. But we can just clear the denominators. Oh, I called that A, that's not so. D. We take D such that D times F and D times G are then integral polynomials. D for denominator. Okay. Good. So we have our polynomials. We have this equation from the Euclidean algorithm. It's just all polynomials. We want the polynomials to be integral polynomials, so we multiply with the denominator, and then we play around. So we plug in for x m over n. Multiply I have different notation here, so I have to think of new letters all the time. Multiply with d times n to the d prime plus d, where d prime is now the maximum of the degrees of f and g. So we can clear out all the denominators there when we plug in m over n. So what we get is okay. So now what we have here reminds us of how we defined capital phi and capital psi. And we also need the greatest common divisor of those two. So let's call that gamma. And now, this n times d prime times f of m over n, this is an integer. And then we have d nd psi of m over n, but this is exactly our capital phi. And then we have this, which is again an integer, and here d times capital psi. And this is d n to the d prime plus d. Okay, I did nothing. I basically just resorted it, and here's no, it's correct. Yeah, I just changed the orders there. So now, if we look at gamma, gamma is the greatest common divisor of capital phi and capital psi, which we have here. So, wait a minute. Let's consider this like this. Because d is, of course, also, d was an integer, so this is also an integer. So now, the greatest common divisor of capital phi and capital psi, since these are integers, has to divide this. So we call it gamma. Gamma has to divide d n to the d prime plus d. This is already pretty good, but it's still dependent on n. So we have to get rid of this n somehow. So because what we wanted is the greatest common divisor of this, which is our gamma. Divides something that is independent of m and n. So we already have that it divides something. It's just not yet independent of n. So how do we get the independence of n? We consider the following. So this is d times we take it minus 1. D times a0 m to the d n to the d plus d minus 1 Okay, so we have that gamma divides d n to the d prime plus d. And where does that appear here? it doesn't appear here, but it appears here and in every term until here. And of course it also divides the left side because it's the greatest common divisor of this capital phi. So it also has to divide this thing. So what we did here is we went from gamma divides capital D. Well, we don't care about this because this is independent of m and n. It only depends on the polynomials. It divides n to the d prime plus d. We reduced the exponent here, but we got an m here, which of course we don't want, but we will get rid of that also. Oh, wait a minute. Wait a moment. Okay, let's continue. I think about the m later. But basically we can just return this procedure just with a -2 here. Repeat this procedure. We get the same here, except that we have the exponent with one decreased. And here d times ADN d prime plus 2d minus 2. And again, we can use that we have this here. Oh no, wait, we still need to get rid of this m before, I think. Just a second. Ah, yeah, of course. We could, we didn't assume it anywhere, but of course we can say that we want m over n to be in lowest terms. And if not, we just make them in lowest terms. So now they have to be co-prime, and of course from this, gamma divides dn to the d prime plus d, And this, we can also conclude that D divides this. Since M and N are co-prime. So now the thing is that we reduce this exponent by the cost of 1a0. And this is what will happen over and over again. We have that gamma divides this. Gamma divides all those terms here. So gamma has to divide this. And since M and N are co-prime, it also has to divide d times a0 times n to the d prime plus d minus 2. And we can repeat this d prime plus d times. And in the end, we get that gamma divides d times a0 to the power of d prime plus d. And we don't have an M, we don't have an N anymore. We only have things that depend on the polynomials. So D was basically the denominator of the Bézout coefficients from the Euclidean algorithm. A0 is a coefficient of one of the polynomials. D is the maximum of the degrees of the polynomials. And d prime was the degree, the maximum degree of the Bézout coefficients from here. So also just one thing that depends on the polynomials. So this will be our R. And we proved part A. Yep.
Why is A0 to the
Because, so what we did here was we went from gamma divides something n to the d prime plus d to gamma divides a0, and here the exponent is reduced by 1. And we can do this procedure again and again. So we do it d plus d times, and then this disappears completely, but every time we get one a0 in addition to that. So we get a d plus d times an a0 multiplied to our constant. Okay, now for part B that I just cleared from the board. So I will state it again. Okay. So we have two bounds. We have a lower bound and an upper bound. And this will be an exercise. In the book, there's also a hint how this is solved. And this we will prove now. And as again, always we can exclude finitely many points, finitely many polynomials, finitely many things that we assume here. And for those, we can just compute the bounds and take that into account when we compute the K1 and K2 for the general part. So we can exclude finite sets. And what we do here, no, we don't exclude anything here. Okay, forget it. I think we don't have to exclude anything here. But again, the statement is symmetric, and we can just assume that one of those is this is the polynomial with a larger degree. Okay. And we take the notation so we can consider this. And we take the same notation as before, so this will be capital phi and capital psi. And we call this zeta. And then the height of zeta will be the maximum of those heights. So the not logarithmic height. Okay. Or no, well, no, it will not be the maximum because we don't know if maybe something cancels out here, but it will be at most the maximum. But from part A, we know, we can take here the absolute value. From A, we know that the greatest common divisor of those two divides some r that's only depending on phi and psi. So we also have something in the other direction. Yeah, because if you think, okay, what can happen here? We can divide by the greatest common divisor of those two. And if we know that the greatest common divisor divides r, and we divide r here, then it's just it's at least as much as the greatest common divisor, but it could be too much. So if we divide it by r, we could make it too small. So this is the lower bound for the height of zeta. Okay. Okay, so, and now we have the maximum of two things. This is always bigger than half of both things. Okay, so instead of the maximum, we take the mean value, and now we go back and just plug in what this actually is. So this was okay. So now a small remark. If we consider the height to the d, so the not logarithmic height, then this is by definition just this. This is just a short remark, and now we go back to this from before. And we want to look at the height of zeta divided by this. So the height of zeta was here, this, n to the d over this, and this is just this. And now we want to look at this as a function in m over n and draw some conclusions. So consider the function phi of t plus psi of t for t and r. So now we have a function here which if we let go t to infinity, this is not 0 because at least what question? It's t. Yeah, because t is our new variable here. If we let t go to infinity, this is not 0 because at least phi has degree d. So it has a coefficient in front of the t over in front of the t to the d. So this is which is not 0. So this is not 0. This is important. So this is either will be a0 or a0 plus b0, but it's not important. Just important that it's not 0. And this is always positive, but I think this is not important. Yeah. So we can find an interval away from infinity that's compact. Let's say from a to b, and of course a and b are not infinity. We can find an interval where p of t is bounded and it's not 0. And we also want this interval to be away from 0 because then also, also without this. This is continuous. We don't need that it's differentiable. The function is continuous because those are all polynomials. And it doesn't vanish because we have absolute values here, everywhere. And the polynomials are not constantly 0. So we can go back to the first semester and use some analysis from there. It has a maximum and a minimum in the interval that it actually, where it actually also takes the value. I think this is basically the first time that we use something from earlier semesters, because I think I kept my promise until now that you don't really need prerequisite knowledge. But of course, first semester knowledge should be there for everyone. So P of t has a maximum and a minimum. In that interval, and we call it we let C1 be the minimum. So P of t is at least C1 for all t in that interval. So how can we use this for our bound? Oh, it's already past 11, and usually it made those sounds, but didn't. How can we use this here? We just finish this and then we have a break. So this was this expression here. So no. No, we don't want this t to be in AB. Well, I'm confused from the time. Maybe we take a break now and then we meet again at 11:15, and then we continue.